All right, so this is our next question. We have c is a value in R. This kind of just means it's a constant. And f is this function, f of x is equal to c times x. So it's this constant times x, just a constant coefficient. And we want to use the formal definition of the derivative, which I will provide on the exam, to show that for any value x equals a, the derivative is equal to c, and that is to show f prime of a is equal to c. Okay, so recall our definition of the derivative, which will be given. I'll just leave it as this, but I'll say it verbally. The limit, I guess, f prime of a is equal to the limit as h goes to 0 of f of a plus h minus f of a divided by h. All right, so usually you can't just use our limit law to push this limit through, because we can see we'll get a 0 on the denominator, and that just means the limit law fails. So we need to do some trickery. Maybe it would be nice to try and simplify this first, so let's go ahead and plug this in. I'll just rewrite it once, and then in the next question I won't. Okay, so this thing is equal to the limit as h goes to 0 of c times a plus h. Right? We're plugging in a plus h wherever we see x. So this entire x value is going to be a plus h. So this is c times a plus h minus c times a. We're just going to plug in a and divide by h. All right, now let's simplify this more. This will be ca plus c times h, right? We can distribute this c through, minus ca divided by h. And look at that, we get some nice cancellation, ca with ca. So this is c times h over h. And then now this guy, because we're within the limit, we can cancel those h's. So we can cancel those h's. So this is the limit as h approaches 0 of c. And the limit of a constant is just the constant itself, so equal to c. And there we go. We have shown f prime of a equals c. Nice. Okay, now our next one. Let's again use our formal definition of the derivative to show that this function for an arbitrary value a is equal to f prime of a equals 2a plus 1. I'm actually going to change this up and maybe make this 2. So f prime of 2 is equal to 5. All right, so using our definition, we have the limit as h goes to 0 of, I said I wasn't going to write it again, but I'm going to write it again, 2 plus h minus f of 2 divided by h. Let's plug those things in. So anywhere we see an x in this function, we're going to plug in 2 plus h with these parentheses. The parentheses are certainly needed. So this is 2 plus h squared plus 2 plus h. This is this thing. And then we need to subtract with parentheses to cover the entire function. This thing here is going to go here. So again, wherever we see an x, we're going to plug in 2. So 2 squared plus 2. And again, make sure you keep your parentheses here around this entire thing. Otherwise, this subtraction sign won't get to this second term, and then you'll get the wrong answer. All right, now let's simplify that. I'm going to use binomial theorem to quickly distribute that, or if you want to just multiply it out, that works as well. 4 plus 4h plus h squared plus, we have that 2 plus 2h still, and I'm going to get rid of the parentheses since it's just addition here. Now I'm going to distribute this minus sign. 2 squared is minus 4, and then minus 2 divided by h. All right, now we get some nice cancellation. This 4 cancels with this 4. This positive 2 cancels with this negative 2. And that looks like that's it. I'm also going to go ahead and combine this 4h with this h. 4h plus h is 5h. So this is 5h plus h squared. That's everything on the numerator divided by h. And then now I can pull out an h from the numerator, 5 plus h. Just double check if I distribute this h through, we get the same thing as we have here. This will be 5h, and then this will be h squared. Good. Divided by h. Now, since we're in our limit, we can cancel the h in the numerator and the denominator, these. And this is just 5 plus h. Now I can distribute our limit to both things, or I can just do direct substitution and see I get 5 plus 0, which is 5. Nice.